There once was a ship that put to sea, and the name of the ship was the Billy of Tea. The winds blew hard, her bow dipped down. Oh, blow, my bully boys, blow. Soon may the wellerman come to bring the sugar and tea and rum. One day when the tonguing is done, we'll take our leave and go. She had not been 2 weeks from shore when down on her a right whale bore. The captain called all hands and swore he'd take that whale in tow. Soon may the wellerman come to bring us sugar and tea and rum. One day when the tonguing is done, we'll take our leave and go.
All right, welcome back to COMP110, everybody. Today we're going to be emphasizing a review of function calls and tracing through examples, as well as taking a look again at conditionals with if-then-else statements. Each week you've been hearing your TAs put on a different rendition of Wellerman. We're probably going to switch that up at some point. If any of you want to contribute music to start class, that'd be great. And our meme boat is continuing to fill up with didDukeWin.com, which we'll come back to later today. So what's our plan for today? Well, we're going to, as I mentioned, practice and reinforce concepts that you'll see on Thursday's exam. So we're gearing up in preparation for that. We'll be looking at diagramming function calls, which were introduced in the asynchronous lessons. We'll be getting more practice with those and trying to emphasize some of the differences between return versus printing, which is one of the common misconceptions and sources of confusion when you're learning how to program. I actually think we're probably not going to have time for named constants today. I meant to take that out of the goals, but we may get to them. But we will be looking at, for sure, procedures, because you'll need that in the next exercise. And these are functions that return none, which is kind of a strange concept, but we'll see why they're useful and where you'll encounter them in programming as we get into it. But first, a couple of announcements. As you all received an email from me via Sakai about some of the quiz topics to be concerned with, the things that we've been looking at in the latest unit include control flow, which we'll be getting some more practice with today, the Boolean operators, relational comparisons between values, equality, inequality, logical operators and or not. That's actually where we're going to start out today. Precedence of these operators. We'll be looking at function calls, and this is really the thing that we're hoping to emphasize and get the most comfortable with in this unit. Calls versus definitions, and looking at what are parameters versus arguments, return types in these subjects. Once we have these fundamentals down, things will continue to add more concepts a little bit more slowly. We try and emphasize these pretty fast and hard out of the gates because they're some of the harder concepts to master, but once you've got a sense of it, you'll be just fine. So we'll be looking at diagrams in more depth today. In preparation for the quiz, and just as a heads up, as you all know, on Poll Everywhere, you'll be able to ask questions, and I'll be checking those throughout lecture. We're going to wait until the very end for questions regarding the quiz. If there's time at the end, I'll get to those. Otherwise, do know that Kaki's having her review session tomorrow. We've got tutoring each night this week. And if there's anything that you really need to know ahead of Thursday, I'll email you about it. One way to prepare for the quiz, besides doing the diagrams in class, is to work on the current exercise that was posted to the course website. So this is how you write function definitions and call those functions. And what's really nice is we're doing this in terms of the exercise you just completed and handed in yesterday. So we did 3 programs without functions, and you just sort of wrote all of your statements in the global scope. Now you're going to try and rewrite those simple little programs using some functions. So you get to reuse most of your code and just tweak it slightly. All right, so we're going to start with a couple of warm-up questions, and we'll have a few minutes for you to think through these 2 questions, and then we'll come back and work through them together. If you're responding synchronously, the address is the same as usual, pollev.com/compunc. If you're asynchronous, there's a link, a bit.ly link on the slide, and you can follow that to respond to these warm-up questions. So you've got 2 sort of complex, arbitrarily long. These aren't necessarily best practice ways of writing Boolean expressions, but they'll give us some talking points in how we think through these types of expressions, precedents, and the operators that are being demonstrated. And what I want to point out here is that we're actually going to be, this is some common syntax that we'll see. Let me actually change this to make this a little bit easier to follow along with. I'm going to do this live real quick. And in Python, you actually have much simpler operators, right? So these operators are commonly used in other programming languages. And in Python, you actually get words. So when you're coming from languages like Java or C, those weird operators like the double bars and the ampersands, you'll see those commonly in many other programming languages. But in Python, you will see and, or, and not written out. And that's actually really nice for interpreting these, right? So when you see those operators written out as such, it's much easier to grok than in a different language, right? So I'm going to give you a few minutes on the clock here to think about what values of A, B, and C would you use in order to evaluate both of these statements as true. Consider these two things independent. They won't have, A, B, and C will not be the exact same for both, but you'll be able to respond to both of these questions on Poll Everywhere with possible choices. All right, we'll have a few minutes for this, and I'll be following along with what your responses are on Poll Everywhere. One more minute on this. It looks like we're about halfway done with your responses. All right, let's talk through each of these. So the first one, over 75% of you got this correct. So let's break this down and let's talk a little bit about how you would interpret one of these types of expressions. And I'm actually going to move this exact same expression that we have here to a new slide so that we have some writing space. All right, so let me just take this expression and drop it in here. All right. And I'm gonna go ahead and do that with the other one as well, because we'll come back and talk through it. Old habits die hard. I should have used the syntax from another programming language there. All right, so we've got this complex expression, and a few things that we've talked about are, the precedence of these relational operators. Just like our arithmetic operators have precedence, so too do these logical operators. And if we wanted to try and be explicit about some of these, we could put some parentheses around each of them. So when it comes to and or, and has a higher level of precedence, right? Or is beneath and on the level of precedence. So we could put some parentheses here. And the outermost and is fine. We could also, so not has higher precedence than and, so this would be evaluated first. And then these are already in parentheses together. So when you're trying to reason through an expression like this was a little bit of a puzzle just to remind ourselves of these operators and the various rules. You oftentimes will try and write expressions that are easier to understand than this. This is sort of a little logical puzzle for us to work through, but let's think through it. So we know that each of these has to be Boolean. A, B, and C are all going to be either true or false based on how they're being used. They're all being used on either side of and or in conjunction with not. And we know that not is a Boolean operator. So one of the ways that you can start is you can think, well, okay, how can we make this true? Well, either side of an or can be true. So I'm actually going to ignore this first side of my expression. We know that it's ultimately going to have to be true, right? Because the and is going to require, the outermost and is going to require both sides of this expression to be true. But let's focus on the right-hand side of the, the topmost and think, well, how could we make this side of the expression true? What would we need to know? Well, for this particular and, both of these sub-expressions are going to need to be true as well. Well, how do we get true out of not C? Well, that means that C must be false, right? So C, we know based on this, is going to need to be false, right? So we've kind of already figured out one piece, and I can go ahead and plug that in on both sides, right? So not C is going to be false for C, but not C is going to be true, right? So I might go ahead and write true here. And then and A or B needs to be true. Well, A or B, it could be either way. We don't have enough to know if both of these are going to be true or just one or the other. So let's go see if we can't make something of the other side. Well, on the other side, if we turn our attention back to the left-hand side of the outermost and, we see we've got A and B and or C, which is false. So we know that this sub-expression, A and B, that must be true. So both A and B must need to be true, right? So A is going to be true and B is going to be true. All right. And over 75% of you got that correct. So great work there. If we wanted to just reason through this and convince ourselves that this all does boil out to true, I'm just going to use T and F for true and false. So true and, let me correct that, true and true, or false, and all of that is parenthetical, and then not false, and A or B, which is true or true. All right, so I'll get rid of this over here, true or true. All right, so let's just start from the innermost parentheses. True and true is true, and so that would be true, and or false. All right, and that's ultimately going to be true, because if either side of an or is true, then it's going to result in true. All right, so true and then on this side, not F is going to be true, and then true or true is going to be true, right? So T and T is true and true, which is true. And then when you get true and true, you also get true. All right, great work there on that question. So the second question, involved some values that weren't just Booleans. So A, B, and C weren't necessarily Booleans, but one of them is. And you all correctly identified that B must be a Boolean. And because it's on the other side of an and, that means that it's going to need to be true in order for this whole thing to be true. So we know that B, once again, is going to be false, right? That's the first thing that we can sort of identify here. Just looking at this very quickly. And we know that because, remember, and is a higher level of precedence than or, so it's as if we have these parentheses, right? Well, what about relational operators? Well, when you see a complex compound, Boolean expression like this, it kind of makes sense that the relational operators have a higher order of precedence than our logical ones, right? Because what would it really mean for 9 and A? That would be kind of, I don't know, that would be a weird thing to try and assign some meaning to based on our understanding of these things. So there's also parentheses, around that are implicit around each of the relational operators. And we know that not has a higher order of precedence than and, right? Great. So we've got some relationships between numbers here. And just like you all practiced in your early elementary days, or middle school days with number lines, I actually think number lines are a great way to reason through some of these relationships that we're seeing here. So let's imagine we've got a number line and we're going 9, 10, 11, 12, 13, 14. I didn't actually need to go that many. All right. And we're saying A is greater than 9. Well, I'm going to use an open circle to say that A is in this direction. So it's not inclusive of 9, but it's anything greater than 9 based on that one expression, right? So it's anything in this direction, right? Oops, I didn't mean to color that in. It's anything on this side of the circle, right? C less than 12. I might use a different color here. So 12, I'm going to draw an open circle and say that C was going to be in this direction, right? Great. Well, A has to be less than C. So whatever we pick out for this relationship, A is going to need to be somewhere lower on the number line than C. So some obvious places might be, well, you could say A is 10 and C is 11. And these conditions would work out, right? So C is in its range, A is in its range, and A is less than C relative to one another. Now, many of you recognize that you could choose multiple answers on this. And we didn't specify whether A and C were integers or floats. And in fact, they could be either or, you could mix them together. So there are a whole, if we're thinking in terms of integers, A would need to be 10 and C 11 for this expression to work out. So I'm gonna assume integers here for a second. So say A is 10 and C is 11, right? But you could have assumed that they're floats, and you could have had 9.1 for A and 11.99 for C, and many, many other possible valid ways of making this a true expression. All right, so let me just real quickly work through this and then look and see if there's any questions on the relational operators that we're talking about here. All right, so A is 10, so 10 greater than 9 and 10 less than 11, or 11 less than 12 and not false. All right, so I've plugged in my values here. Not false. All right, so let me just go ahead and once again add some parentheses around our relational operators. These are what we're going to need to do first, and as well as this not false. And then maybe I'll use pink to say, okay, well, let's then look at this side of the expression and this side of the expression. There are other ways that you could have made this true, potentially, as I mentioned, because of the number ranges. All right. Okay. Great. So let's see. Now I'm going to pick, let's just start from here. 10 greater than 9, true. 10 less than 11, true. And, right, so that's going to be next. And then 11 less than 12, true. And not false is true. All right, and then true or true. And I wanted to emphasize here that, remember, the or is not one or the other, like we often think about true or the or word in English. The logical or if both are true, it's still going to evaluate to a true value. And so we would end up with true here in those responses. All right, let me take a look at questions and see what's come in. So the quiz is on Thursday, right? Yes, the quiz is on Thursday. When I say an exam or a quiz, they're all assessments just the same. All right. If you weren't able to fix all of your mistakes on exercise 1, this is a good opportunity to work on those. You'll want to come and make sure that you get full credit for exercise 1. Remember, the late policy is such that you can turn it in today and at the end of the semester still get full credit. So do try and move through exercise 1 and then focus on exercise 2. There's a question that has to do with the assignment. What is to do? To do is a note that you'll make in code, and this is something that you'll come back to when you are ready to work on some specific area of code. So we'll often drop to do comments that are saying, here's where you're going to focus your work, and you can delete that comment line and work on a solution at that point. All right. Does the not operator always yield a true or false statement, not a number? That's correct. So the not operator will only flip a Boolean to be the opposite of what it is. So not true is false, not false is true. All right. Can you explain the line break binary operator on Gradescope? I'm going to hold on a Gradescope question until later. I'll come back to that. True or false is true. That is correct. And let's see. All right. There's a couple other questions on some specific scenarios of like what happens if you did true for all of the operations on the first one. Come work with us in office hours to see if you can make another solution drop out. But if I were to just very quickly try and take on that question, so not C needed to be true. And so you couldn't have true for false here, or sorry, you couldn't have true for C. If C were true, then not C would be false, and then false and whatever this is going to be false. And then because they're conjoined with an and there, the whole thing would have been false if C were true. All right, so that's a quick few logical puzzles to get us warmed up and thinking about Boolean operators. The next thing I want to do is turn our attention to a code listing. And in this code listing, we're going to produce a stack heap diagram. And I want to work on the beginnings of this diagram with you and have you follow along with that. And we'll have some time for you to move through this example and try and figure out what its output is and what the frames that you'll need on the call stack are based on our previous set of videos. So we've got a code listing here, and I'm going to go ahead and set up, my stack. And this is our call stack where our function state will be kept track of, and my heap. And for all we know right now, the only thing that will be in our heap are going to be our function definitions. Okay. When we first begin a program, we know that the built-ins like print and input and stir and abs, they already exist. For our diagramming purposes, we're going to ignore those. So we're going to start with just what's in our globals frame. We know that those things exist, but our concerns in diagramming are really to understand what's going on in the code listing we're looking at right before our eyes, right? And so you're always going to have one of these globals frames. And let's see what happens. So on this first line, just a doc comment, nothing for us to do here. This is just naming this program jump around, right? On line 4, we encounter a function definition. So whenever you encounter a function definition, what we're going to do is set up, okay, well, the name yes, no in globals now refers to the function definition that is on lines 4 through 10, right? Now remember, we're not going to look inside of that function and worry about what it's doing yet. We're just saying, hey, we've encountered a definition of a function, and we're going to mark that down in our globals frame. Same idea with this function definition. So there's a function named did Duke win? And that is a function that exists on lines 13 through 19. So that's where its definition is found, lines 13 through 19. All right. Once again, we're going to ignore what's inside of this function definition until we are evaluating it. All right. And there's nothing, until we get to line 22. And on line 22, we see that we are declaring a variable named Duke in globals, and its value is 87. Right? On the next line, we're declaring a variable named UNC, and its value is assigned 91. Right? And now we have the very interesting point in our program, which is on line 24, we encounter a function call. Right? Did Duke win is a function that's being called, and it's being given 2 arguments. So for this first example, I want to help you remind you of some of the steps of setting up this function and get you into the did Duke win function, and then turn it over to you to complete this diagram and check in on when you're done on poll everywhere, and then we'll do it together. All right. So when we encounter a function call, how do we know that we encountered a function call? Well, we have the name of some identifier, did Duke win, followed by some parentheses, and potentially some values inside of those parentheses, which will be our arguments, right? But the name is always going to be followed by parentheses to signify there's a function call, and you're not going to see the def keyword, right? So this is not a function call, this is a definition, but this is a function call, right? It turns out print is also a function call, but it's a call to a built-in. So we're kind of going to ignore the fact that Python has some built-in functionality around the print function. We're not going to concern ourselves with that. We're focused entirely on this call right here. So the first question we ask is, have we seen a definition for this function? Did Duke win? Well, we look in our globals frame and we say, sure enough, we did. We know what did Duke win is. It's actually bound to the function defined on lines 13 through 19, right? So we saw it up here. Great. Then we need to fully evaluate our arguments. So what is UNC? Well, UNC, we had previously seen a variable. It's declared to have a value of 91 as its assigned value. Great. So the 91 is going to be our first argument. And then we look, what is Duke? Duke was assigned 87, right? So we have 2 integer arguments. And now we have to ask, is this a valid function call based on the definition of the function, right? Well, did Duke win as a function, and it defines 2 integer arguments, or sorry, 2 integer parameters, right? So the function definition has our parameters, the function call has our arguments, right? And so, yeah, that checks out. So we've sort of met the criteria for a valid function call. We've got a name that we've seen before that's bound to a definition. We've got arguments that match up with the parameters. So let's set up our frame. So when we set up a new frame for a function call, we're going to say the name of the frame, or the name of the function that this frame will belong to, is did Duke win? And it's going to have a return address. The return address is, where did this function call occur? It occurred on line 24. Right? So on line 24, that's where we're going to go back to with the result of this function call. Okay. And now we need to set up our parameters. So parameters are like variables that will exist in this frame. So UNC is being assigned 91, right? So this 91 is being assigned to the parameter UNC inside of the did Duke win function frame. And 87 is being assigned to Duke, all right? So Duke has a value of 87, all right? Now we've moved through the steps to establish a frame, and the interpreter is about to jump to line 14. And it's at this point that I'm going to turn it over to you to try completing this diagram and checking in on poll everywhere once you've got a solution. This sequence of steps that occurs is in its own right an algorithm, and someone implemented these steps in a programming language in order to make Python. And so this practice that we're getting, thinking very deliberately about these steps that go into an algorithm such as setting up a function frame call, it's the same type of thinking that you'll see when you're trying to write programs that solve problems that you'll encounter. So I'm going to turn it over to you. We'll have probably 5 to 8 minutes, depending on the responses that come in. Just let me know when you've finished up, or when you've reached a point that you don't know what to do next, and we'll work through this together in just a moment. 2 more minutes on this, and then we'll continue on. Some great questions that have come up. I'll get to those as soon as we jump back in. All right, great work. It looks like many of you were able to successfully navigate this, and some of you are stuck, and that's totally fine too. We're seeing many concepts combined for the first time here outside of the introduction videos that were on Thursday. So I want to address a couple of questions that came in. First, the difference between the stack and the heap. What is that all about? Well, the stack is where, when we're working in functions, or as you've been working so far in the semester in the globals frame, it's kind of where our local variables are. And we'll have more to say on each of these stack frames when we have some examples to demonstrate this. But you can kind of think of it as like local working space for a function to do its job that's kind of isolated from other functions, so that you don't have to worry about accidentally interfering with something you didn't intend to. It's sort of like a cubby for a function call to do what it needs to do in isolation. The heap is going to be for values that we have in our programs that are longer lived. And the only thing that we have in the heap so far are these function definitions. And the reason why we write function, or FN, that's short for function, and then the lines that they're on, is this is sort of our like hand wavy way of saying this is a function that can be found on these lines in our program. We'll see examples for why we would even make note of that later in the semester, but we're just getting comfortable with this practice. Behind the scenes, the actual Python interpreter would take our code and convert it to much more sophisticated, what we call data structures and representations behind the scenes, much more so than we would care to diagram in something like this. So we're just saying this is where a function definition is found. That's what that line means. All right, there's some great questions about if FB, or what is if B. I'll come back to that when we get to that point. All right. So then there's this question that I do want to talk about before I continue on here. This is actually one of the common confusions of learning function definitions versus calls. So the question is, why do we skip from the first def yes no to did Duke when, and then down here to where we set up these variables before jumping back inside of this? Well, imagine that you are flipping through a recipe book in your kitchen. Each of those recipes is a lot like a function definition, right? And because you skipped past a page, like you may have noted, like, hey, here's a function I might want to use, or here's a recipe I might want to cook, here's a recipe I might want to cook. You're not cooking those things yet. You don't actually like go and follow the instructions. You might kind of read through them and have a sense of what they're going to do, so you're prepared and you know what you might need, but you're not going to follow those instructions yet, right? It's not until we call a function, which is what we're seeing down here in this expression, that we're saying, hey, actually go inside of that function definition and follow through its steps, right? So it's this call to did Duke win that jumps us into the body of that function. And let's pick up from there. So the first thing that happens inside of did Duke win is we print jump up with a question mark. So I'm going to have my output somewhere else. So my output, to keep track of that, is jump up. Okay. And then we're doing something kind of interesting. We're saying, okay, let's reassign the Duke variable. Well, which Duke variable are we talking about? We now have two of them in our call stack. Remember, when we are talking about a name and we're using what's called the process of name resolution, we have to look in our current frame on the stack. And the current frame is whatever function we're currently evaluating. It's in our diagram, it's going to be the function that has yet to return. All right. So here, the frame that we're talking about is did Duke win? And we're looking at the Duke variable that has a value of 87 here, but not the one that's in globals. So there's two separate Duke variables in our program's memory right now. And the reason why we have the second one is because we had a parameter named Duke. This sets up a local variable for us to use. And what we're saying is, okay, Duke minus UNC. So Duke is 87 minus 91. That results in -4. And we're taking -4 and we're reassigning it back to the Duke variable. All right, so Duke in this frame is now -4. Notice that we now have two different values for our Duke variable. And this is totally fine. There's no problem with this whatsoever. All right, so we've reassigned Duke. And now what we're saying is, we have another variable declaration statement. For my purposes, I liked to go ahead and figure out what is the result of the right-hand side of the assignment statement before worrying about my variable here. But if you want to pencil in that 1 is going to need some space, we're going to need to store a string here, whatever the yes/no function call gives us back, then you can do that. That's fine too. So we reach a function call expression. Once again, this is the second function call expression within this program that we're seeing. And what do? Well, our steps are, one, do we know what yes, no is? So we look in our current frame and there's nothing there named yes, no. So it doesn't exist in this local frame. And if it doesn't exist in a local frame, then you check your globals frame, right? We're going to skip to globals and we see, have we seen something named yes, no before? Yes, it's the function defined on lines 4 through 10. Right, great. So we know that this exists. And then we need to fully evaluate our arguments. Well, there's only one argument here, Duke greater than 0. All right, so -4 greater than 0. What is that? Well, that's going to be false, right? So this is as if we're calling the function yes, no with an argument of false, right? So this expression here, Duke greater than 0, that evaluated to false. And so now this is the expression that we're trying to evaluate. As a reminder, arguments are special and they're different from parameters because we can use expressions like this. So this is a Boolean expression. The interpreter needs to evaluate this to true or false before we make the function call. All right, so we've checked the name of the function. We've evaluated our arguments. Now we need to check and see, is this argument, does it correspond to the parameter that yes, no defines? So yes, no is a function. It defines a single parameter b, which expects a Boolean. So yeah, we've got a valid function call. So let's go ahead and set up our frame for evaluating yes, no. We reach a function call. We follow the exact same steps we did before. So we're going to say there's a frame call for the function yes, no, and its return address is, where did this call occur? Well, this is where we were. We're going to come back here with an answer, but this is where we're going to come back. We're going to come back to line 17 with the return value of calling yes, no. All right. And we need to set up our parameter is a variable. It's b, and we established that this was going to be false, right? Because Duke greater than 0 is false, always, right? So now we've established our frame and we're ready to jump in, right? Well, we reach another print statement. Here we print the string jump up with an exclamation point. All right, let me get out of the way here. So we've now output jump up, question mark, jump up, exclamation point. And we reach this if statement that many of you had a question about. If B, that looks kind of funny. Aren't we used to seeing, if something's greater than another, if something's equal to something else? Well, remember, when you use an if statement, the expression that you're testing, that test condition, just needs to be a Boolean value. Well, B is Boolean, right? So B is just a variable name that is our parameter, and it's going to be true or false. And so we ask ourselves, okay, well, what is B? So we look in our current frame, and our current frame is this yes, no frame that we're evaluating, and B is false. So we're asking if false, right? And when we encounter an if and the test is false, we jump over the then block, so we don't do this, and we reach a return statement, right? So this is the first time we're returning in this program. All right, well, what do we do when we reach a return statement? There's another sequence of rules that we discussed in the previous videos, right? So we're going to keep track of that. We're going to say that the return value of this function is no, or this function call is no, right? So we enter our return value, that's RV. And what are we doing with that? Well, we're sending it back to line 17. So we're taking the string and we're sending it back to line 17, which we kept track of as the return address. And so this yes, no expression evaluates to the string no. And ultimately, the string no is assigned to the variable 1. All right, so let me pause here for just a second and take a look at questions after mentioning one other thing. All right, so the other thing I want to mention is that because the return statement is special, it's not like the print statement, it's not like other statements we've seen. Once we reach a return statement in a function call, we ignore anything that comes after it, right? So we could never actually reach line 10 in this program. In fact, you shouldn't write a line like line 10. It kind of doesn't have a meaning. I wanted to include it in this example to give you a reason to distinguish between returning versus printing. So when we hit a return statement, this function call's job is done. We enter our return value, we send that back to line 17. And then what's going to happen is we just completed line 17, but the current frame we're working in is now the did Duke win frame, right? Why is that? Well, we finished the work of this yes, no frame. Now what the computer would do is it would actually reclaim this. It would erase it. But for leaving a sort of trail of work in our diagrams, I'm just going to leave this on the slide. And because we can see that this frame returned, we're going to assume that its job is done. And our focus goes back to did Duke win. All right. When a function is called multiple times, what do you put as the return address? Well, I'm going to show you that in the next example is actually going to take that question head on. And the short story is each time you call a function, you have a new frame for that function call. So what we'll see is there's going to be multiple frames for multiple calls to the same function. So we can have multiple frames for yes, no, if we were to call it more than one time. All right, great question. All right, so there's a question of, I'm confused why it returned no and not yes. So B was false, right? So if B is false, and that means we're not going to go into the then block of this if statement. We're going to skip over it. There's no else block, right? So we just continue on right after this line, and the next line is we return no, and that's why the return value would be no. All right. So I'm going to bring this one home, and then I'll take a look at the questions again in just 1 second. All right. So next we reach the print statement jump around. So I'm going to add to my output jump around. And then we reach a return statement for the did Duke win function. And what are we returning? Well, we're returning the current value of 1. Well, when we reach a return statement that has an expression like this one, we need to look up what is the current value of 1. It's no, right? So the return value of did Duke win function call is going to be the string no, right? What are we doing with the string no, right? Well, to know what you do with a return value, you look in your return address. And this is telling us, hey, the call that got us into this function call in the first place came from line 24. So we're going to send that back down to here. And effectively, we're saying, okay, we'll print out whatever the result of calling the did Duke win function, and that was that was the string no, and so we print out no. All right, and then there's nothing left for our program to do, and our program would be completed. So the expected output here is jump up, jump around, and then no for did Duke win. All right, there are some other questions that have come in. Let me take a look at those. How come there is no else block? Great question. So I wanted to give an example that was similar to the one at the end of the video that included the return statement to say that if B were true, right? If we called yes, no with B as true, let's just imagine this separately. We didn't in this program, right? Then what we're going to do is we're going to, if B would be true, we would go into the then block and we would return yes. And then we wouldn't return no, even though it's the statement right after the if statement, because as soon as you reach a return statement, a function call's job is done. We enter the return value, we send it back to where that function call originated, right? We could have just as easily written, else, and then indented return no by one level. And in fact, I would probably encourage that in the early days of using if and else. I just wanted to emphasize that there's a big difference between return and print, right? And a big enough difference that I think before we jump to the next example, I'll want to make a few notes on that. But let me just see if there are some other questions here that I should address. So the print statement that has get down on line 10 is never printed. That's correct. This line can never be reached because this return statement is here. If you were evaluating this code and trying to give someone feedback, you would tell them that, hey, you shouldn't have written that there because it doesn't make any sense. It'll never happen as written. Would the output be in quotes? So when we talk about output, the output, it's always going to be string or textual based. Like everything that we send to our terminal as output through the print function is going to be text. So you don't have to include string quotes around your output, even though they are technically all strings, even if we printed numbers. We do encourage and require that when you're keeping track of your memory or your variables on the call stack, that you put quotes around your strings so that we know, the data types that you're working with. All right. Wouldn't if B always output true because false is a Boolean? That's an interesting question. So remember, just because this is a Boolean, that doesn't mean we know anything. We know whether it's true or false. So you're correct that this has to be a Boolean, but B can either be true or false. And so it turns out we could, if we called yes, no with true as the argument to the function call, then if B would be true and we would return yes, right? This, in your early days of programming, lots of first-time programmers really like to write, if B is equal to true, right? We encourage you to convince yourself and spend some time anguishing over whether or not you actually need to write is equal to true when B is a Boolean, because B is already true or false. So if true is equal to true, that's true. If false is equal to true, that's going to be false. But it's kind of redundant to have to specify this, because B already, if B is a Boolean, its value is either going to be bound to true or false based on what you stored in that Boolean variable. Great question. All right. How did we know that B was false? Well, when we made the function call right here, we asked, is Duke greater than 0? We had previously established that Duke was -4. So -4 greater than 0 is false. And that's what became the argument that we called yes, no with, right? So this is where that function call originated. And we can kind of look back at our diagram and know this, right? Because yes, no, we see that the return address was line 17, and that's where the argument would have been set up. All right. Okay, so there's a question about the yes, no function call that occurred here. And hopefully what I just said helped to clarify that. But if not, I think the next example will. All right. I just want to make a few quick notes about print versus return that you all have so that we can address this head on. All right. So when it comes to print versus return, these are two concepts that feel like they're very similar as you're getting started with programming, but they're very, very different. All right, so I want to talk about return first. And return is a special function, or sorry, a special keyword, not a function. Special keyword. And you could also call it a statement because it is its own kind of statement. It's a line of code that has specific meaning. It's a special keyword or statement that completes a function call. And returns a value back to the caller. And the caller is what we often say to refer to the function call expression. So if I want to be a little bit more formal, I could say, I'm going to just use fn call expression. So the function call expression. And in two abbreviations you'll see us use frequently in this course are fn for function and expr for expression. Right? Print, on the other hand, is a built-in function. That sends output outside of the program. So what do I mean by that? Well, you can imagine the terminal as something that exists in your environment, right? So the terminal is where you started your program. And if you wanted to have something display in your terminal after you run it, Python -m and then in your script name, you have to print it. And so print is actually, it's sending information outside of the program, whereas return is saying, okay, we're evaluating our program and I want to send some result somewhere else inside of my program so that wherever that function call expression occurred, I'm returning a value back to it. Remember, we think of functions as sort of this contract where the caller can say, hey, if I give you the right arguments, the right types of arguments, what you will give me back ultimately is the type that you declare as your return type. And I know what I can do with that return value once you give it to me. All right, there's a great question on what is the difference between parameters and arguments. Let's take a look at that in terms of the next code listing. So the next code listing that we're going to discuss, I'm going to have to make this just slightly smaller. Let me see, I'm going to remove some new lines here. Technically, as you are writing functions, Python stylistically has a convention of placing two new lines between each of your function definitions. And so this rule, just like some of the linting rules that you've come to love or hate in the autograder, linting helps us maintain a consistent style across all of the programs that we write. And we didn't actually come up with any of the linting rules that you all are subject to in the grading of these programs. These are written by the Python community and accepted as like, this is just what good Python style is. And a linting tool like the ones that we use helps you make sure that you're following best practices with style. And in the early days, it's the most annoying because you don't necessarily know what are the expectations of style. And it's often you're much faster to learn those style rules by trying and then seeing where the feedback is rather than seeing a list of all of the rules unrelated to code that you've actually written. So that's why we style code in the way that we do. And that's what linting is all about in the grading portion. All right, so we've got a function, three functions here, and a couple of things we're seeing for the very first time. Main is a funny function. It's one that is defined to have no parameters and has a return type of none. And we see that it returns none. We'll come back and talk more about a function that returns none after we've thought through this a little bit more. But for now, just think of none as a special kind of value. The other thing that's special here is this if statement down at the bottom. And whenever you see something that has 2 underscores surrounding it, in Python, we call these dunderscore names or dunder names. I kind of like it. It makes me think of Dunder Mifflin in The Office. But it's a special variable that has unique meaning in Python, and the double underscores say, in the Python programming language, we're kind of reserving this variable for our use. You shouldn't name something double underscore name that is unrelated to how what we understand that to mean. And so the name variable, we'll talk more about the specifics of it, but when I actually run this program, name is going to be assigned the string main. Later, we'll learn cases where that's not true, but for the purposes of evaluating this program, and as you'll see in the next exercise, this is something that will commonly come up in almost all of the programs that we write moving forward. When we run our program, this will be true, and this function call will occur on line 22. So let's set this up, and then I'll talk just briefly about the difference. Actually, before I talk about the difference, before we set this up, let me talk about the difference between arguments and parameters and address that question. We can see there's a function call right here, f of x, right? X in this scenario is an argument, and we know that because it's an expression. It's referring to this variable that we set up on the line before, right? VS Code is actually trying to be kind of helpful, and it's highlighting this x as related to this x. They're the same one, right? So that x is an argument, whereas this x, when we actually define a function, when we define the function and have what's inside of the parentheses that follow the function name, those are our parameters. These are not expressions, right? This is more like a variable declaration where we're saying x is a variable whose type is integer. And so what we're establishing is that g has this expectation. If you want to use the g function, or if you want to use the x function, you've got to give me an integer. Inside of the function, that integer is going to have the name x. And we'll see some of the funny rules about that soon. One of the other things that came up as a question earlier was what happens when 2 function calls are made to the same function. So you can call a function as many times as you want in a program. And in this example, we'll actually see that the g function is called twice. And so there will be 2 separate frames for g. Well, let me help you get this one set up, and then I want to give you a few minutes to try working through this on your own, and then we'll work through it together. So there are another few important concepts to take home in this example, and we try and use some of these more complex code listings in lecture as challenge problems to really emphasize some of the common misconceptions about how a function is evaluated. All right, so we've got a stack. This is where our frames and where our sort of our working variable space is, and my heap. All right, and our globals frame is going to enter each of our function definitions, right? So we see a definition for main, and main is the function defined on lines 3 through 7. We see a definition for a function named g. G is the function defined on lines 9 through 12. And we see a function f, and f is a function defined on 14 through 18. And I'm just going to write function after this. All right, so we've got our global set up. And then we're going to assume name is indeed equal to main. So this is true. And on line 22, we reach our first function call, right? Because we haven't dealt with a function that doesn't have arguments and parameters, I'll help you get this one set up. So this would be a function called a main, and the return address is line 22. And there are no parameters to set up. So that's all we would do to get this function frame set up. And now we're ready to jump into the function main. All right. We can tell that this is a function call because we have the name of some identifier followed by parentheses, and there's no def keyword in front of it. But sometimes it's harder to identify a function calls when you don't have arguments, right? So your job is going to be to pick up from line 5, and let's spend another 5 to 8 minutes taking this as far as you can. One thing I'll give you a quick hint on, because this is a common misconception and one of the primary purposes of illustrating this example, is when you're evaluating a nested function call expression. So this is like in the mathematical sense, g of f of x. Well, you really need to work your way out. You need to figure out, well, what is x? And then, well, what is f of x? And go evaluate that function call. And then finally come back and evaluate g of whatever f of x evaluates to. All right, I'm gonna turn it over to you and clear the responses on whether or not you finished. So check in when you think you've got it or if you are stuck. Two more minutes on this one, and then we'll work through it together. All right. So some great questions have come in on this particular tracing as well. If you are still working through it, that's totally fine. As long as you've made it through a couple of frames, hopefully you're getting a feel for how this is coming together. If not, let's keep working through this. So we've entered the main function and we've reached a variable declaration. So we're setting up a variable in the main frame named x. It's being assigned a value of 2. Right? And on the next line, we're reaching this nested function call expression. Now there's a great question that came up. It's like, hey, Chris, I thought you said in the previous set of videos that you can't call a function until after it's been defined. So how are you able to call g or f here? Well, I mentioned that there's a pretty cool trick that we can do in order to sort of make it easier to structure and order the definitions of our functions however we want. And it turns out, well, okay, let's think through the same rules we talked through before. If we're trying to call the f function, do we know what f is at this point in our program? Once we've reached line 6, once we're trying to actually evaluate this, just as the computer would. So we look in our main frame, that's where we're currently working, and no, we don't know what f is there. But then we ask, okay, well, if we don't see something in main, we're going to check our globals frame next. And sure enough, we've got f is a name that we've already encountered the definition of. And it's the function defined on lines 14 through 18, this function down here, right? So there's f. So there's this clever trick. The reason why we make the call to main at the very end of our program is so that we've already loaded up all of our definitions of these functions into memory. And that means that when we actually write those functions, we have more flexibility. We can refer to functions who, yeah, sure, at line 6, the first time the interpreter was trying to understand this block of code, it didn't have f of x. It doesn't know what f is yet, but that's okay because we're not actually following that recipe, right? We're not jumping into this function and we don't worry about what's inside of it until we actually call that function. And then we're going to go and do those steps. And at that point, we better have a function defined. However, if I had called main right here, or even better, if I had called it, down here, if the call to main had occurred on line 8, this would have errored out and we wouldn't have known what f or g is at this point because we had yet to encounter those definitions, right? So this is one of the reasons why we use this structure. We call main at the very end and that gets us into this point. All right, so we reach this call, f of x. Well, x is 2, so we're calling f of 2. We ask ourselves, does f exist? Well, we just convinced ourselves it does. Does 2 line up with what it expects? Well, its parameter is x. So yes, 2 is going to be f or assigned to x in the f function. So I'm going to set up a frame for f. It's going to have a return address of line 6. So that's where this function call occurred. Right? That's where we're going to go back with the result. And x is going to have a value of 2. All right. So we've established our arguments or our parameters inside of this function call. And now we're ready to jump in. We reach a print statement. So I'm going to set up my output. And the output is f of, and then we're concatenating string of x. Well, string is one of those built-in functions that we're not going to diagram, but string of x is 2, so f of 2 would be the first line to print, all right? Then we reach a variable declaration statement. We say x times 2, that's going to be 4, is assigned to a variable y. Now, this is an important statement to understand, is happening in a specific context. It's happening in our current frame, which we're working in f's frame, right? So we set up a variable y, and y is going to be assigned a value of 4, right? So now we have two variables in the f frame. Y has a value of 4, and we reach a return statement. But before we can return, we need to fully evaluate this expression. What is g of y? Well, this is like the same as saying, what is g of, and then because y is 4 in this function call frame, what is g of 4? So we reach another function call, and we have to ask ourselves, does this function, is it valid? Have we seen a function named g? So we check, do we know of any g's in our f function or our f frame? No. And then we check globals. Do we know of any g's? Yes, it's the function defined on lines 9 through 12. So this is a function that we've seen the definition of, and we're going to call that function. Does our argument, which is 4, correspond with its parameter, which is x and the integer? Yes. Okay. So we have all the things that we need in order to call g. So I'm going to set up a frame for g, and its x value is going to be assigned 4, right? We're taking that 4 that we had set to y, and we're saying, okay, copy 4 in to be x inside of g's context, right? So let me make that a little bit cleaner. X is 4, all right? And our return address is line 18. That's where we're going to go back with our result. All right, so we jump in. What do we know? We reach another print statement. So we're printing here G of, and then concatenating X. Well, which X are we talking about? And this is where you kind of get the sense that knowing the current frame that you're in, which in a diagram like this is always going to be the lowest frame that has yet to return. So notice there's no return value in G, so this must be our current frame. And in this frame, X is 4. So G of 4 would print out. All right. And then we reach a return statement, and we're ready to return a result back to line 18. So what's our return value? Well, our return value is going to be 4. X times 2 is going to be 8. Sorry, we need to fully evaluate this. So 4 times 2 is 8. So my return value is 8. And what are we doing with 8? Well, that's why we keep track of this return address. The return address is line 18. So we're sending 8 back to this function call, right? So this was the frame for G. And now we're going back to return G of Y. That's the same as saying return 8, right? So my return value for our current frame, right? The current frame is the lowest one on the stack that hasn't returned. It's F. Return value here is going to be 8, right? So what do we do with this 8? Well, we return that back to line 6, all the way back up to main. So you notice we're jumping into functions and we go back in the same order. It's kind of like climbing the stairs in a building and then going back down them. You have to, if you're going up the stairs, you're going to go back in the opposite order. And so now we're back into main, and f of x evaluated to 8, right? So this is as if f of x here is 8. So g of 8 is what we need to do next, right? I'm going to bring this last function call home, and then we'll look through questions and take those, right? So g of 8 is another function call. We've already seen g. We know that g does expect an int argument. So g has a return address of line 6, right? And x for this call to g is going to be 8. So notice another important thing that we wanted to illustrate here is this is the second time the g function is being evaluated, and we have another frame for it. That's totally fine, all right? So we jump into g, and now we print g of 8, right? Because that's what the current value of x in the current frame that we're working on in g is. And now we're going to return 8 times 2. That's 16, right? So what are we doing with 16? Well, we enter the return value, 16, and we send that back to line 6, right? So back up to main. And those are the steps that we called f in turn called g, and then that all resulted in calling g one more time. And ultimately we're back in main, and we reach this line 6, and we print just the value that was returned, which was 16, right? So this expression in g led to 16, and ultimately this call would print 16. That's the last line of output here. We reach return none. So in main, I'm going to have a return value of none, and then my program will be complete because there's nothing for me to do after this point in it. All right. So that's officially the end of lecture time. And I know many of you have other classes and obligations, but just like we would do in an ordinary lecture hall, if there are questions that people have, I'll take those on for a few minutes here, and you're welcome to stick around. But I'll remind you that if you have questions about doing these diagrams, tutoring is the absolute best place to come for help with them. And second to that, not as a slight to Kaki, but just because when you're in a large review session, it's harder to get one-on-one help than it is in tutoring. But if you can't make tutoring, come to Kaki's review session or watch the recording of that. All right. So let me take a few questions here that are at the top of the list. How does it read? Okay, so we addressed the question of how the ordering of g of x, g of f of x is able to actually evaluate, even though the definitions of these come after. That's because of the way the main function is defined and set up. We've already seen those names and we've entered them in our globals frame. All right. So this is actually a great question. So the question is, why are we writing g of y here, but g of x up here? Now remember, this is one of the distinctions between arguments and parameters, right? So y is an argument, and as an argument, it needs to fully evaluate, right? So y is going to evaluate to let's see, when we called f, y was 4. So this is the same as saying g of 4. Y only really had meaning inside of this frame for f, right? That's the only place where we had y defined. And when you make a function call, we're saying, okay, here's a specific value for this expression. In this case, it's 4. And I'm assigning that to the parameter x, which is a variable in the function called a g. And so x is going to have, a value of 4 when it gets evaluated. The names of your parameters are only matter within the function definition itself, right? They have no meaningful relationship to other things. It's just a coincidence that in main we had a variable named x, and in G we had a parameter named x. All right, so just to give you a quick example of this, I could have named this x parameter, UNC. That'd be a bad name because it doesn't really have meaning. But if I change this to UNC within this function definition G, it would be totally fine, even though in other places we used x and y. So that brings me back to one question that was really good that I didn't get to take related to the did Duke win. Could we have just used A and B here? Yes. So we could have just done something like this, where we have A and B as our parameter names, and they're kind of, but it's harder for us to know what this function expects without reading it more closely. Or alternatively, we could have, named these variables home and away. And actually, I think it was away and then home. And that would be totally fine too, right? Because the variables that are in our globals frame are unrelated to the variables that are in our did Duke win frame. What we're doing is we're passing specific values. We're copying those values in related to the ordering. So the ordering here matters. All right. Does every function definition end with a return? One other thing that, since we didn't get to talk about it before the end of class, I'll spend some more time talking about procedures next week. But no, so one of the cool things about none is that when a function returns none, you don't have to have a return statement at all, and it would be totally fine, totally valid. And in fact, that's typically what we would expect in a function that returns none. It's the same, it means the same thing, but it's kind of, if you're not returning me anything in this main function, why are you going to the trouble of having that statement there? So we would ignore that. All right, so another question. So in order to call a function, you have to put the arguments as values for parameters in the expression. Yes, that's exactly the intuition. Whenever you want to call a function, like if we want to call f here, we've got to give it some expression as the argument that's going to be an integer. So here, when we called f, we gave it x, or whatever x's value was, and x's value was assigned, it was 2, so that worked out just fine. But that's exactly right. Same idea here. Did Duke win expects 2 integers, and here, did Duke win away and home? Well, those are 2 integer values based on the declarations of these variables, and that's totally fine too. All right. So if we have multiple nested function calls like this one, you are going to evaluate from the inside out. That's correct. So it's just like, a parenthetical arithmetic expression. We want to evaluate our argument first, and then go to the next function call that's outermost, and then the next one after that. All right. Why is our stack divided into 3 parts? Let me bring that back up. So I'd encourage spending some time with the third video and tracing through it step by step, where we talk about how the stack gets set up, piece by piece. Every time you encounter a function call, so the first function call was main, we set up a frame for main, right? We saw a function call here for f of x. That's what led to this function call frame. Within f, we reached this call to g of y. That's what led to this function call frame. Ultimately, those returned back up to main. Then when we reach this function called a g, that's what led to this last one. So every time you have a call to a function within the code listing, it's going to result in the sequence of steps being carried out that lead to a frame on the stack being established. And so that's why those are there. So there's this question of what's going on with these lines. pretty soon we're going to learn how to write functions that we can use in other programs. You've already seen this where someone in the random library wrote randint. And so we say something like from random import randint, right? What we're doing is we're using one function from somewhere else. Pretty soon we'll be able to do that with our own files. So we can say, hey, I want to write some tests for some functions I wrote in my program, and I want to be able to import them. But I don't want to have to run the whole program when I do that each time. That nuance is more than we need to concern ourselves with right now. For right now, just assume that the name variable will always be main. And once we start writing larger programs, we'll see that that's not true in some more specialized scenarios. But this is what we call an idiom in Python. And it's something that you'll commonly see as a well-structured program. And we'll also typically have our main function at the very top of our programs because it serves as somewhat of a table of contents. Like here's sort of an overview of what's about to happen in our program, and more of the details will be in the functions that follow. All right. Yes, so when you have nested function calls, as I mentioned, you're always going to work your way from the inside out. We have to know what G's argument evaluates to, which is the call to f of x. We have to go fully evaluate f of x before we worry about calling g. And that order will ultimately lead to like the output that you see here. How did we end with 2 G frames? All right, so the brief way of getting to this point is, so again, let me just trace through this sort of in a more intuitive sense. So we see g of f of x. So this call to f jumps us into the f function. We see that this call in f, we're jumping into g. So we've got to go figure out, well, what was g of y? Okay, well, ultimately g returns. It doesn't make another function call. So we go back to where we came from with some returned value. We go back up to where that f call occurred. And then here's where the second G call occurs. So this G call jumps us straight into G. And then that returns, and so that's why the ordering it was what it was. We go FG, back to F, back up to main, and then back into G. This is one of the most fundamentally challenging parts of processing function calls. And I would encourage spending some time with this example. Try typing this out and adding additional print statements if you want to convince yourself that it works in this way. But once you understand these rules, they apply the same in many different circumstances. And so when we learn recursion, we will have even more reason to make use of these kinds of rules. Recursion is much easier once we're comfortable with these types of semantics. How do we know how to move through the program? So as we've been learning and taking notes on, there's just a sequence of steps. There's an algorithm that the processor is going to do a certain thing whenever it sees a variable declaration or an assignment statement. It's going to do something else if it sees a conditional. It's going to do something else if it sees a function call. And so building up an understanding of those rules is helpful for knowing how a program is going to be evaluated. And that will help us ultimately be able to write correct programs and understand the code that we're writing and the implications of it. And being able to trace through these programs step by step like this is a valuable skill that we find is very helpful in making actually writing programs more understandable. So there's a question of why was main the very first frame, even though it's the last function call. Remember, every time we reach a definition, we plug that definition's name and a reference to its definition into our globals frame. So we move through each of these pieces. We add those definitions. Main is bound to the function on 3 through 7, G 9 through 12, so on. And we don't do anything inside of those functions. It's not until we reach this call to main that we say, okay, now it's time to make our first function call. And that first function call is what leads to this frame being established. And that's what sort of kicks off our program. You'll see this commonly, and you'll get more practice with this in the next exercise. When you return a value, the RA is always in the next frame you're supposed to work on. Yeah, so whenever we return a value, so for example, the return value here, 16, is being sent back to line 6, right? So line 6 was in the main function. And if we were to go back to this point of our program and say that, okay, well, main hasn't actually finished up, we would see that the current frame on our stack, as I mentioned, that's always going to be the lowest frame that has yet to return. So this frame's returned, this frame's returned, this frame's returned, this frame is not returned. So we're going to be in line 16, and the frame that we're working in is this one. It's main's frame, where X is 2. And the return value of G of this expression was 16. And so that's why 16 would be printed out. So you're not necessarily like, remember, this call to G happened after these two frames had completed. So we're actually sending, that return value back to the next frame that hasn't returned is the way I would think about it. In that case, it was main. All right. Can you nest function definitions? That's a great question. The short answer is yes. And there's some really cool things you can do with that. We won't talk about that much. Actually, I don't think we'll talk about it at all in 110, even though it's, I find it really cool and really fascinating. But yeah, if we were to have a nested definition, like define another function in one of these functions, what would wind up happening is, that name would only make sense inside of the frame for that function call. And so how you bind it would be different, but it is possible, and it's pretty cool. You can look into it. Yep. Do you still put new variables within a function definition or in the globals area? Great question. This will be the last question, and then I'm going to end stream. All right. So here we have f, and that's this function. So we were working on this function, and we had yet to return. And let's imagine I just back up to here. I'm not going to carry this whole thing forward, but let me just address this question. So this is a variable declaration statement, right? So we're getting comfortable with this syntax. We have the variable name, the type, and it's assigned some initial value. So the question is, where do we actually store this value? And this is where knowing what your current frame is important. You're going to hear me repeat these words over and over again, but the current frame is the lowest frame that hasn't returned. That's at this point in our program, that's this one, right? And because it hasn't returned, when we reach a variable declaration, that means I'm going to declare y here to have a value of 2 times 2, which would be 4, right? Now I want to contrast that just to make this a little bit different. Let's imagine we go all the way back. So we've just loaded our definitions, and now we're about to make this call. If just before main, I had something like, X is a string assigned hello, then X would have been in globals because that's our current frame, right? So where you encounter that declaration of the variable, which frame you're currently working in, that's where you're going to set up space for it. All right. Well, these were some great post-lecture questions. Again, diagramming and understanding function calls is one of the most challenging concepts we'll encounter in this course. It's got the most steps, but that's why we start early and try and practice comfort. We have the whole semester to get even more comfortable with these concepts. And once you're comfortable with these steps, a lot of programming opens up to you, and we'll be able to write some much more interesting, highly applicable programs. All right. See you all at the review session or in tutoring, and back here for the quiz on Thursday.